So last class we started rigid body dynamics, and here this rigid body dynamics is of two phases. One is the Torck and again the parallel and perpendicular theorem. Next one is that is the moment of inertia. All this is considered to be one phase. So this is the first phase, and when you are coming to the second phase, it is the angular momentum and conservation of angular momentum, and that is the velocity and the time and acceleration of a rolling body along the inclined plane. So that is the second phase. So far we have discussed that is the theory of this Torck, parallel and perpendicular theorem, and again the moment of inertia. So in my last class I was explaining to you that is the moment of inertia of the different rigid bodies, and I almost gave more than 20 formulae regarding that all that different rigid bodies. So first of all, I have taken the uniform thin rod, and again circular ring, and again the circular disc, and thereafter it is the solid cylinder and the hollow cylinder. Next again rectangular lamina, and for the square lamina also, and after that it is a solid sphere and the hollow sphere. So all these were discussed in the last class. Now we are coming to that is the main level test, that is the main test problems. So that is not the advanced level test problems. These are the main test problems which are looking for that main test, and moreover these problems are useful even for the NEET students, also. So those problems will be discussed now. Here the first problem we are coming, that is a roller of weight 3000 newtons. So first I read this problem. A roller of weight 3000 newtons has a radius of 0.5 meters. So that is a roller of weight, that is a 300 newtons. So 300 newtons is there, and its radius is the 300 newtons is here, and that is taken from this 300 newtons, and thereafter its radius is given 0.5 meters. And in addition to that, that is has to be dragged along over a brick of height 0.2 meters. So that's why h can be taken as the 0.2 meters. And thereafter, what is the minimum horizontal force to be applied at the center of the roller? What is the minimum horizontal force to be applied at the center of the roller? Now this is considered the roller, and its weight is 300 newtons is given, and radius is given that 0.5 meters. Now it is to be dragged over a brick. So now this is the brick to be taken, and its height is the height of the brick is 0.2 meters. So that's why it is the h is taken. Next, when it is to be dragged like this, a horizontal force is applied about its center. So this is the horizontal force. Now this is the center of the roller is this one. Now the question is, what is the force to be applied? That is, what is the minimum horizontal force to be applied at the center of the roller? At the center of the roller means now this roller is to rotate about this point. So this point can be taken as a point of rotation, and we consider this is the P. So this is the P. So with respect to that P, that roller is to be dragged. So that's why we have to take the movements about this point P. So this roller is to be dragged like this. With respect to this point P, it is to rotate. Now there are the two torques are acting on that roller. So those two torques are, one is that is a torque due to the applied force, and the second one is a torque due to the self weight of that roller. So torque due to the self weight of that roller means already you know that is a torque is nothing but the moment of force, which is nothing but the force into perpendicular distance about the point of rotation. So that's why here it is the torque due to, so torque due to self weight. So torque due to self weight, it is nothing but that is the 300 newtons is there, and again it's a perpendicular distance about the point of rotation. So about that point of rotation, this is taken as the r is here, and again this is taken as the r minus h. This is the h is already there, that is the height of the brick. So that's why this is the r minus h is there, and this is the radius, and again the r minus h is here, and again this can be taken as we consider this the x is here. So that's why it is the self weight is the 300 newtons, and into the perpendicular distance about this point of rotation, that point of rotation is that P. So about that point of rotation, that perpendicular distance is nothing but x. So 300 into x is there, and x is to be determined separately. Now it is a 300x is there. That is the first equation, and this is the torque due to the self weight of the roller. This is the torque due to the self weight of the roller. and thereafter torque due to the applied force. Torque due to the applied force is, that is a torque due to applied force. Applied force is, and that can be taken, that is a force into, here the perpendicular distance about the point of rotation is r minus h. So r minus h to be taken, this is the second equation. So these are the two torques simultaneously acting on this. Now when the torque due to the applied force is greater than that of the, so that is the torque due to the applied force is greater than that of the f of r minus h greater than that of this torque due to the self weight, that is the 300x, then only this roller can be dragged onto this over this brick. Then only this roller can be dragged over this brick. When the torque due to the applied force greater than that of the torque due to the self weight, then only. Here you are supposed to find out only that minimum amount of the force that is to be applied. So that's why for that we are taking it is the f of r minus h is equal to, because our requirement is only the minimum force. Our requirement is only the minimum force. Its meaning is it is the force which is the minimum force. It is the force which is the minimum, and to roll this body over this brick like this. So that's why it is the f minimum into r minus h is equal to 300x to be taken. And here r minus h is there, that you have to find it. And already you are given that 0.5 and h is the 0.2 is here. H is the 0.2, and then this becomes the r minus h is equal to 0.3. So that's why here it is the triangle is taken like this. So it is the 0.3 is there, and already it is the 0.5 is here, and x is nothing but the 0.4, because it is a 3, 4, 5 combination of a right angle triangle. So that's why 0.3, 0.5 and again the 0.4 is there. So that's why r minus h, in place of that we can take it is the f minimum is equal to f minimum into, that is the 0.3 to be taken, and after that 300, and here it is the x is the 0.4 also to be taken. Next 0.4. Now f minimum is equal to, it is the 300 into 0.4 by 0.3 is here, and it is the answer is that 400 newtons. 400 newtons. Its meaning is when you are applying that much of force, that is the 400 newtons, then only it will be ready to roll over this, it will be ready to rotate over on this brick. So that's why it is the minimum amount of the force. Here this is the application on the torque only. Here it is the application on that torque, moment of force. So that's why we are coming to the next problem. That next problem that depends on, that based on moment of inertia. So here in this case, a straight uniform road. We are coming to the next problem. So now it is the first problem is over. Now we are coming to the second problem. So in this second problem we are taking, that is a straight uniform rod of length L and mass m is there. So this is the L is here, and again the mass m is here like this. Now here it is bent into a square. The mi about an axis passing through the center and perpendicular to the plane. So that's why it is bent into a square like this. So that's why each side becomes m by 4, L by 4 like this. Each side becomes m by 4 and the L by 4. Now you are supposed to find out the moment of inertia about an axis passing through the center and perpendicular to the plane of this frame. So perpendicular to the plane. So in this case, that is the L is the uniform rod. It is bent like this into a square. So that's why each side is the m by 4, L by 4. Now you are supposed to find out the moment of inertia about this point passing through that. Suppose if at all it is a frame is taken and about this axis. Here in this case you cannot apply that formula which is coming for the square lamina. Suppose for the square lamina you may get confused to apply this formula. So INA is equal to m of L square plus L square by 12 is there, that becomes the mL square by 6. You can't apply this formula. Why? Because this formula is applicable only for the lamina, not for the frame like this. This formula is applicable only for the lamina, not for the frame like this. So that's why here you can't apply this formula, and here you have to take that is the moment of inertia of all the sides to be determined with respect to this point O. So in this case it is the m by 4 is there, L by 4 about this point O. About this point O means, so first of all, now this is the frame is there and it is to rotate like this. Now in this case two axes are appearing. These are the two axes are appearing. One is about the given axis. This is the axis about which you are going to determine the moment of inertia, And the second one is each side is rotating about its own axis also. Each side is rotating about its own axis also. About its own axis means, suppose if at all this frame is taken like this, now you are taking the frame like this. In this case, now you are supposed to find out the moment of inertia about this one, as well as each side is rotating about its own axis also, like this. When it is rotating, that each side is rotating about its own axis. And now the two axes are appearing. One is here and another one is here. So when it is being rotated like this, that each side is rotating about its own axis, about its natural axis also. So because of that, that's why here you have to apply the parallax theorem, because the conditions for that parallax theorem already are there. So that's why two axes are there. One is the natural axis of that side and again about the given axis. So that's why we are finding the moment of inertia of each side now. So for that we are taking the I is equal to, that is the INA plus mr square is there. So m dash r square is here. So it is the INA plus m dash r square is here. This is the moment of inertia. This is mi of each side. Mi of each side. That becomes, it is the I is equal to INA plus m dash r square is here. And here it is the INA means, as you already know, this is rotating about its own axis means, now it is nothing but the moment of inertia of the uniform thin rod about its natural axis. It is the ml square by 12. So that's why we are applying that formula. INA is equal to ml square by 12, m dash and again the L dash square by 12 to be taken. So m dash is nothing but the m by 4. And L dash is equal to, just now it is given, it is the L by 4. So that's why L by 4 whole square and by 12 is also there. Now it becomes, it is the m by 4. Now it is the L square by 16 and again as usual it is the 1 by 12 is also there. Now it is ml square by 4 into 16 into 12. So once again I tell you, it is the moment of inertia of each side about its natural axis. It is the m dash L dash square and by 12 is here. Here we have applied the parallax theorem, because the two axes are appearing there, but you are going to determine the moment of inertia about this axis only. It is the INA is equal to m dash L dash square is there by 12, m dash is the m by 4, L dash is the L by 4 whole square by 12 is there. Then you got this answer, that is the ml square by 4 into 16 into 12 is here, by 12 is here. And here we are applying that is the ml square by 4 into 16 into 12 is here. And we are coming to the next part. And the next part is, as you already know, it is the m dash is equal to m by 4. And r is the distance between the two axes. R is the distance of separation in between the two axes, which is nothing but L by 8. So this is the R. So that's why it is the L by 8. So that's why L by 8 whole square to be taken. L by 8 whole square. Now it is ml square by 4 into 16. That is a 64 into 12 is there. And thereafter it is the ml square and 64 into 4 also to be taken like this. 64 into 4. And after solving you are going to get that is moment of inertia of each side. All this is the moment of inertia of each side. So now if you want to find out the moment of inertia of the entire frame about this given axis, about O, then mi of not the each side, now it is the mi of entire frame. So mi of total frame about O, that is nothing but the I dash, we consider this one. So that's why it is the I is equal to 4 into I dash. Why? Because there are the 4 sides. There are the 4 sides are there. So that's why 4 into I dash is there. After solving, then you will be getting that answer is the ml square by 48 is there. So that's why it is the answer ml square by 48 that comes. So once again I tell you, now here there are the two axes are appearing. This model is very important. This model is very important, application of the parallax theorem. Here when the frame is rotating, first of all you should not get confused. Here you should not apply that formula for the rectangular lamina or the square lamina, because it is not the lamina, it is only the frame only. So that's why you have to find out the moment of inertia of each side. In that case I dash is equal to INA plus m dash r square, and INA is this was the formula that you have to apply. And again after getting this one you have to apply it here. Then this is the moment of inertia of a total frame about O. This is for one side, and for the total 4 sides is this much, that is the ml square by 48 is over. Okay, now this problem is completed.